Greetings and welcome back. Today we're going to be kind of tying everything together that we've done with NMR and talking about how do we interpret a signal. So again, the whole point of these methods of spectroscopy is not to figure out what a spectrum looks like, but to be given a spectra and say, what does all of this mean? So let's say, for instance, that I've got a peak that looks like this. And it is showing up somewhere around like 3.4 ppm. And we can do its integral. This will make more sense maybe if you see the book. But we can integrate out how many hydrogens are in that environment, all of that good stuff. What does all of that mean? And how can we use this to figure out what the molecule looks like? So when you look at any peak, I think the best way is to take a systematic approach. Given an NMR, the first thing you're going to want to say is how many different environments. And that's going to interpret as how many signals do we have on the NMR. Right, today, we're going to be looking at these signals individually, so looking at signals one at a time and saying what do each of these signals mean. All right. The second thing is the chemical shift. What does the environment look like? How many neighbors is something else, but what is nearby in terms of functional groups? The third thing is the integrals. And remember that the integrals tell you the number of H's in the environment. The fourth thing is the splitting, or the peak multiplicity. And the splitting tells you the number of H neighbors. So those are our four things, and if you have no idea what any of those are, I suggest you go back a little bit before we talk about these today, because today we're going to be talking about doing these things backwards. All right, so let's jump in. I'm going to give you an example. I'd like you to see if you can figure out what this means. So let's do the one that we did on that previous slide, which was we got this peak, shows up around 3.4 ppm. And when you use the NMR to integrate that, where it does this and it kind of figures out what is the area under that curve, it comes out to be 2 H's. So pause for a second and see if you can figure this out. See if you can figure out what all of that means. All right, here's what I would do. I would start off with the integral. I think that starting off with the integral is the simplest thing to do. So if the integral is 2, that means that there's 2 H's in that environment. Not neighboring, but just in that environment. What is most likely, by far, is that this is a CH2. You all know that a CH2 has 2 bonds, one on each side, and it's got 2 bonds to hydrogen, because all carbons have 4 bonds. So right off the bat, that gives us some really good information that we can start from. We almost certainly have a CH2. It is of course possible that if you have an integral of 2, you have 2 identical CH's somewhere, but let's look for the simplest solution first and go from that, which is that if you have an integral of 2, it's almost assuredly a CH2. All right, what does 3.4 ppm tell you? That's what I would do next. So the chemical shift is between 3 and 4, and that tells us that we are most likely a CH next to an O, or a CH next to an N, or a CH next to a halogen. We don't know which one, and there's no way to tell which one it is. So you can hazard a guess, but I would just keep your minds open, keep your options open, and say it's one of those things. So it's probably next to one of those. If you remember, we can use IR and mass spec to tell whether we have a halogen or a nitrogen or an oxygen. Therefore, if you're coupling this with one of those, you can probably figure out what that is. So for instance, if you got an alcohol peak, it's probably the O. But we don't know based on the NMR, so go with what you do know, which is that there is some type of heteroatom over here. So I'm just going to say O/N/X on one side. All right, and the last thing is the splitting. So the splitting, if you have 4 peaks, it's a quartet. And remember that the way that it works is the number of peaks is 1 higher than the number of neighbors. So if you have a quartet, you have 3 neighbors. If you have a triplet, you have 2 neighbors. If you have a doublet, you have 1 neighbor. And if you have just a single peak by itself, you have no neighbors. So in this case, it's a quartet. So in that case, what that means is that we have 3 H neighbors. And how does this fit in to what we have up here? Right? So here's our 4 things that we did. What we're looking at is this peak right here. We know that it's got an O or an N or an X on one side. If it's got 3 H neighbors, then they must be on the other side. Therefore, they must have a CH3 next door. So that actually, just based on looking at this peak, tells us a whole lot about the molecule. We know that we've got a CH2, and we knew that it was a CH2 because it integrated to 2. We know that it is next door to an O or an N or an X. Again, we don't know which one, but we could figure that out using some other methods. And we also know that because it has 3 neighbors, it's a quartet, that it has a CH3 next to it. All right? Therefore, that tells you a whole lot about this molecule. We don't know what goes on in this direction. If it's an O, it could be an OH, and that could be the end of the molecule. If it's an X, then it's just, whatever, a Cl over there, and that's the entire molecule that we can tell. But it could be an O to, let's say, an ether, and then we would have to figure that out. But again, to figure out what else is over there, we would have to do more work. There might be more signals in the NMR to interpret. But based on that one signal, we can get a whole lot of information. So here's 3 examples that I'd like you to try on. Just pause this and work through all of them, or you can go through them one at a time. I'll go through the answers one at a time, of course. But see if you can figure out roughly what that's telling us about, what each of these signals is telling us about the hydrogens in that environment. All right, let's start off with the top one. Because it integrates to 1H, we know that it is just a CH. There are no hydrogens on the neighboring bonds. It's at 9.8 ppm, which is quite curious. That's way away from what we're used to seeing. So this takes a little bit of recollection or you looking it up. But 9.8 ppm falls somewhere in the region of an aldehyde. So this hydrogen is probably, well, is definitely part of an aldehyde. Interestingly, it's got a triplet. A triplet, of course, means that it has 2 H neighbors. How could that guy have 2 H neighbors? Well, as weird as it looks, because it looks like that H couldn't have possibly any neighbors, that H is on this carbon, and the neighboring carbon must be a CH2, because it's a triplet, it's been split twice, so it has 2 neighbors. We don't know what happens further on down this molecule, and that peak or this signal doesn't tell us. But what this signal does tell us is that we are a CH that's part of an aldehyde and has a CH2 neighboring. So that gives us good information about that part of the molecule. Don't try to put all these 3 together. They're completely unrelated examples. All right, the second one down here, because we have a 3H, it integrates to 3. It must be a CH3. Right off the bat, that's great. Good stuff. 1.1 doesn't tell us anything fancy, but what it means is it's not close to anything remarkable. It's definitely not next to a halogen, it's definitely not next to an alkene or anything like that. It's really just a CH3 all by itself. But it must be next to something, because a CH3 needs to have one more bond. We see that we have a doublet. What does a doublet mean? Doublet means that you have 1 hydrogen neighbor. And with 1 neighbor, it means that you must be next to a CH. So this is my signal right here, CH3, but it's got to be next to a CH. That can't be a CH2, it can't be a CH3, it's just a CH, and so it's probably got carbons over here. We can't say that for sure. We know those aren't hydrogens, and likely if those were oxygens or nitrogens or halogens, then our signal would probably not be so low. It probably wouldn't be at 1.1. So this would be my best interpretation of this molecule. It's a CH3 next to a CH that doesn't really have anything else complicated attached to it, at least at that point. All right, lastly, we have something that integrates to 1, so that means that we have a CH. It's at 1.5 ppm, which again isn't really much. It doesn't tell us much. It's just not next to anything fancy. But it's got 9 peaks. 9 peaks means that it has 8 hydrogen neighbors. And that is something. So if you haven't gotten that far, see if you can work that out. But this is a CH, and it's got 8 neighbors. You can't, of course, have a CH8, but because this is just a CH, you know that that carbon has to have 3 more bonds. On those 3 bonds total, there need to be 8 total neighbors. So let's just start drawing them in. 8 neighbors, 8 adds up to, none of these could be CH4s, so it's got to be a CH3, which is 3, and a CH3, which is 3 more, so that's 6. Meaning that it can't be another CH3, that would be 9 neighbors. So we've got to have a CH2 over here to give us 8 neighbors there. So this is pretty interesting. That tells us, again, a whole lot about the molecule. We don't know what's happening down here because that CH2 needs to be attached to something else. But actually that peak right there, that signal, tells us a whole lot about this molecule. Right? So this is where splitting, combined with integrals, combined with the location of the chemical shift, tells us a whole lot, and we can really start to tease out what these molecules are. So next time what we're going to be doing in class, not this upcoming class, but the class afterwards, is we're going to start putting these things together. But I'd like you to be able to reliably figure out all the information you can from individual signals, and then we'll start putting them together later into full molecules. So I'm going to give you a couple to try on the next slide, and we'll go through those in class. All right, so I'd like you guys to try these 3 out. These will be the first things we talk about in class. So remember, look at your multiplicity, look at your number of hydrogens from your integrals, and look at the chemical shift and try to put them together. Thanks, and I'll talk to you soon.